Hello, everybody. My name is Sean Slonwhite. I am the Regional Rep Director for Daikin Comfort Technologies for the Atlantic Canadian region. I look after mainly the VRV and light commercial products in the Atlantic market, New Brunswick, Newfoundland, PEI, and Nova Scotia. I'd like to thank the Canada East chapter of the Association of Energy Engineers for having me here today to talk to everyone about the transition to low GWP refrigerants. As we'll see today, there's many paths to decarbonization. Build better buildings, green construction materials, load reduction, electrification. But like Gina and Jeff kind of alluded to when they were up here, they touched a bit on mechanical systems and the refrigerant inside those and what is the impact of those refrigerants to global warming. Especially when you have a global warming potential of 2,000 times that of CO2. And as a matter of fact, you know, the GWP performance of the refrigerants in these systems is so bad that global governments from around the world have come together and signed agreements to phase down their production. In not 10 years' time, like 2 years' time. So I'm here today to talk to you about what the phase down looks like and why Daikin has chosen R32 as our next gen refrigerant for most of the North American product, including our VRV systems. Okay, so what we're going to do is we'll go over like a very simplified history of refrigeration, look at new low GWP refrigerants, including A2L classification, the current and future outlook on codes and standards, and what the impacts will be for VRV and VRF systems. Maybe first thing I should do is check, just like so I have a reference point. Is everyone familiar with VRV and VRF acronyms, what they mean? Just a quick show of hands. So VRV and VRF systems, they're mechanical systems. DX, so we're directly expanding refrigerant within the building. We're moving energy within the building in the refrigerant network. With variable speed compressors. So what we use as refrigerants inside of them is very important. So looking at, sorry, I'm kind of trying to balance the laptop and the mic here at the same time. So looking at an overly simplified history of refrigerants, the history of refrigeration goes back hundreds of years, but it's widely accepted that Willis Carrier is the forefather of air conditioning as we know it today in homes and businesses. The problem with the first refrigerants was that they're very dangerous. They were highly toxic, flammable, combustible gases. And it wasn't until 1928 that the General Motor Company first synthesized chlorofluorocarbons, which were a low toxicity, low flammability refrigerant that made suitable for use in residential applications and really widespread. By the 1970s, air conditioning was accepted pretty much globally. We saw 50% of cars coming off the manufacturing lines had air conditioning systems, and R22 was the refrigerant of choice for unitary and residential air conditioners and heat pump systems. And then something major happened. Does everyone recognize this picture? So this is the hole in the ozone layer. We've known about the existence of the ozone layer since the early 1900s and its role in protecting the Earth from UV rays from the sun. It's been monitored actively by the British Antarctic Survey since the early 1950s, and they recognized that there was a seasonality to the thickness of the layer. It degenerated a little bit in the summertime and then regenerated in the Arctic winter. In the 1970s, there was a major concern because they noticed that the rate of degeneration was greater than regeneration over the winter months. And then in 1985, to the shock and awe of the world, it was discovered there was a hole in the ozone layer. So this was a pretty big deal internationally. It led to the Vienna Convention later that year. So Vienna Convention for Protection of the Ozone Layer. International community came together to agree that immediate and meaningful action was required to avoid further destruction of the ozone layer. They put together an action plan and a timeline for phase out of ozone depleting substances, which was the Montreal Protocol, and it was universally ratified in 1987. The phase out plan started in January 1989, but the production and use of R22 wasn't impacted right away. We saw a major change in 2010 with R22 product, as new products coming into the market with R22-based refrigerant were banned. And then we saw a further change in 2020 when the refrigerant itself was banned, so no new R22 refrigerant into the market. R410A was accepted as the best alternative, given that it had similar thermodynamic properties to R22, but it was zero ozone depleting. So why are we switching refrigerants again today? So it's important to note that while ozone level depletion and increased global warming are both tied to human activity, they're two separate issues. So by the 1980s, we knew increased levels of CO2 from fossil fuels were adding to the natural greenhouse effect of the Earth's atmosphere. But global warming potential of refrigerants at that time wasn't well understood. So zero ozone depleting, non-toxic, and low flammability made A1 refrigerants like R410A an appealing alternative to the ozone depleting CFCs and HFCs. But in 2013, the atmospheric CO2 hit a value of 400 parts per million for the first time in over the last 400,000 years. So this was acted as another wake-up call for the global community, similar to the discovery of the hole in the ozone layer. The 400 part per million threshold in 2013 prompted cooperation of the international community to come together again and act. This is the 2015 Paris Agreement that we saw referenced in the previous presentation. So it recognized the urgency of the problem of global warming, and it was signed by more than 180 countries. It targets raising surface temperature of no more than 2 degrees Celsius, and we're already 1 degree warmer. So one step in the Paris Agreement was the Kigali Amendment to the Montreal Protocol. Because the Montreal Protocol was regarded as such an effective international effort to limit the impact, it decided that the Kigali Amendment should be made to the Montreal Protocol. So this is what the Kigali Amendment kind of looks like. This is HFC phase down. So to mitigate global warming, the Kigali Amendment phases down, not phases out, the use of HFCs, and specifically HFCs with a high global warming potential, so greater than 700 GWP. This is what the phase down schedule looks like. So you'll notice that 2024 was the first major step down in the production of new HFCs over 700 GWP into the market. In North America, we're challenged with an 85% reduction of high GWP HFCs by 2036. Regulatory bodies across North America have been working to finalize the last production dates for new equipment containing R410A. So it's important to note that this is a phase down in production of new refrigerant into the market. It's not a phase out, and it doesn't take into account reclamation and recycling programs. So what are the choices for low GWP refrigerants? And what are the considerations? So GWP is one part of the equation for evaluating refrigerants' direct environmental impact. So it's looking at a pound of refrigerant versus a pound of CO2 and what is the kind of equivalent measure for global warming potential. But we need to make sure that we're making the right choice, also considering the 3 R's, so recycle, reduce, and reuse. The two main refrigerants in the North American market kind of pinned for replacement of R410A is HFC R32 and HFC R454B. These are both low flammability refrigerants, and they have relative global warming potentials of 675 and 466. So I'll take this moment to note that R32, although new to the North American market, is a proven commodity globally. It's already used. It's got an install base of over 230 million units in the world, over 140 countries, and it's used by 50 different OEMs already. So when we talk about recycle, reduce, and reuse, R32 is a single component with open patents, meaning that multiple manufacturers can produce the product. and it has a robust supply chain. It also means that R32 will be easier to recycle once reclaimed or reuse on the same site. So systems can be charged with a refrigerant in liquid or gas form, and in the event of a slow leak within a system, it can be topped up without reclaiming and weighing in new refrigerant. So there's no temperature glide associated with the R32 product because it's a single component. We're already seeing R32 in the market because R410A is a 50-50 blend of R32 and R125. And the R454B alternative also contains R32 with a blend containing R134. So GWP is a direct impact of a refrigerant leak compared pound to pound to CO2, but it doesn't take into account other important metrics like system efficiency and refrigerant effectiveness, so how much capacity delivered per pound. Because R32 is more effective and efficient refrigerant than R410A, Daikin estimates that R32 systems can be engineered to deliver similar system capacities using up to 40% less refrigerant charge. So while a 20-ton system might require 100 pounds of R410A, an equivalent system with R454B would be closer to 95 pounds, and R32 would be closer to 70 pounds of refrigerant. So lowering the equivalent GWP by multiplying the factor of which we're reducing the total system charge. So you see that this brings things much closer together in terms of a total equivalent GWP performance. So R32 and R454B are both part of a new classification under ASHRAE 34. They're labeled A2L for flammable refrigerants that burn very slowly. So the burn velocity on these refrigerants is less than 10 centimeters per second. They're both low toxicity, so the toxicity is not a concern, it's the flammability. Now, when people think about flammability, they kind of picture in their minds big explosions. Propane, for instance, as a refrigerant, that's something that people think about. When you go out and you start your propane barbecue and you kind of take your time to light it, you have a mini explosion. A2L refrigerants are not like that. So when we compare new A2L refrigerants to existing A2 and A3s like propane and methane, we can see a dramatic reduction in the burn velocity. So it's about 5 times slower than methane and about 6.7 centimeters per second. So when ignited, it roughly takes about 15 seconds for that refrigerant, the flame in that refrigerant to travel a distance of 1 meter. That's a pretty slow burn velocity. So the second consideration, of course, burn velocity is one consideration, but how readily are you able to ignite that source? So ignition requires 3 things. 1, oxygen. It requires a concentration of flammability substance greater than the lower flammability limit, and it requires an ignition source of greater energy than the minimum ignition energy. For hydrocarbons such as natural gas, they need relatively low concentration and low energy to ignite. A2Ls require much more energy to ignite and a much higher concentration. So if you look at a concentration of propane at 2%, that's something that you can ignite. For our A2L refrigerants, and specifically R32, you need a concentration of at least 14% or higher in order for that mixture to be ignitable. Okay, so now moving on to codes and standards. ASHRAE 15 and UL 240, they're both published and allow A2L for use in large charge systems. CSA B52 has also been published in 2023. And now we're just kind of waiting on the adoption of the province of that code so we can roll out the R32 systems. This is what the map looks like as of today. All the green provinces have either evergreen policy on B52 or they've already adopted it. So basically, as soon as a new version of B52 is published, it becomes active in that province. You see that BC and New Brunswick, both of those provinces are due to adopt by the end of this calendar year. That's kind of when they accept the code change. Nova Scotia, PEI, and Nunavut are both, all three of those are unspecified when they will accept it, but it's expected that they will accept by the end of this year. So looking at ASHRAE 15, so this is something that should be common knowledge for most of the people designing VRV and VRF systems. It's kind of our biggest challenge with oxygen depleting refrigerant. So this is non-toxic, but it will displace the oxygen in a room. So we have to worry about how much refrigerant we can release into an enclosed, occupied space and protect human safety. With R410A, that charge is 26 pounds per 1,000 cubic feet, and that's at sea level. It has to be corrected for elevation. So basically, when you look at your system charge, you have to be below that limit in order to be code compliant. When we look at ASHRAE 15 for R32, it's a much bleaker picture. Out of the gate, the allowable concentration limit is a quarter of the lower flammability limit. Remember, that's 14% concentration. So in 1,000 cubic feet, we're allowed 4.8 pounds of refrigerant. So that's 1/5 of what we were dealing with R410A. That's a pretty scary number for a guy like me that's making his living selling these systems. But the good news is that we do have now prescriptive mitigation measures, which we didn't have before for the A1 refrigerants. Specifically looking at refrigerant leak detection. So if we have leak detectors at the indoor units and we're able to turn on the fan, we kind of mitigate that heavier than gravity effect of refrigerant. If we mix the air in the room, we can double the charge allowable. So now we're at 9.6 pounds per 1,000 cubic feet. It's still, 2.5 times less than what we can do now, but we're starting to get a little bit better. If the project has a refrigerant concentration limit, if we've still exceeded it with this fan mitigation measure, we do have two paths. The first one is a ventilation path, so we can look at designing an outside air system to ventilate the space, either mechanically or naturally. But it's designing and implementing a separate 100% air system only to act as a safety measure seems like it's going to be too costly from a viability perspective. So what we think is going to happen, is most likely to happen, is safety shutoff valves. So this is another new thing with ASHRAE 15, is a new concept around releasable charge. So instead of looking at full system charge, we're able to look at how much refrigerant is releasable into the space with these safety shutoff valves. Keep going backwards there. So the releasable charge, the definition is the portion of the system refrigerant charge that can be released into a space as a result of a single point of failure. So we have to take into account the charge within the indoor unit, the charge in the pipe between the shutoff valve and the indoor unit, and how much charge will travel through that pipe in the time it takes the valve to shut, which is normally around 30 seconds, or that will be the standard, will be 30 seconds. So we have kind of 3 different mitigation measures using these safety shutoff valves. We can do a centralized option. So this is looking at safety shutoff valves built into the branch selector or branch controller box, basically the point at which we have a heat-cool zone. The way it would work is that a leak detected at the indoor unit would bring on the indoor unit fan and also shut off the safety valve. This is probably going to be the most practical option because it'll come built in from a manufacturer, and it'll be all part of their design software. So when you're putting in your pipe lengths in your selection guides, it'll give you a quick yay or nay, is this system gonna be compliant or not? All those calculations will be included in the selection guide. The second option is individual safety shutoff valves at the indoor units. So this would be a similar shutoff valve, but built into the indoor unit or the fan coil itself, working on the same principle as the first. If we have a leak detection, that shutoff valve will shut. This will definitely give us the minimal releasable amount of refrigerant into the space, but it's questionable whether the practicality of this, because space is already limited within the indoor units. So the third option might be to do branches within a refrigerant network. So we're looking at zoning the refrigerant network itself by either field supplied or manufacturer supplied shutoff valves. This might be the most practical in terms of a initial cost, but it's going to be more involved in terms of engineering and load calculations because it will likely not be calculated within the software. So even with the same refrigerant classification, not all A2Ls have the same application flexibility. So the refrigerant concentration limit of R32 and R454B are similar, but the system charge of an A32 system is about 16% lower than R454B. So combined, it means that a R32 VRF system with the same capacity can be installed in a space roughly 20% smaller. So looking at the table below, we have the base refrigerant concentration limits, 4.6 for R454B versus 4.8 for R32, and then the effective charge calculation, and then the LFL with bringing on the fan. So what does that mean for real-life examples of VRV applications? So this is our first example. We're looking at R32 in a school. In this example, we have one VRV system serving 8 classrooms. We use an average classroom size of 900 square feet with 9-foot ceilings, a multi-port branch selector box or branch controller box at one end of the building, and that simulates a higher charge scenario. The total system charge will be 75 pounds, which is equivalent to 90 pounds in an R410A system. It would be a 20-ton outdoor unit with 10-port multi-port box, and then 3-ton ceiling cassettes for the classrooms. So we've lost the animation on this slide, but without a safety mitigation, so the initial no bringing on the fan, looking at 4.8 pounds per 1,000 cubic feet, the only room that's applicable or that is within the refrigerant concentration limit would be the hallway. In this example, if we're able to bring on the fan and all of a sudden all of the rooms are within the refrigerant concentration limit of 9.6 pounds per 1,000 cubic feet. The second example we'll look at would be R32 in a hotel. So this is, hotel can be a tricky application for VRV and VRF, specifically because in the micro hotel rooms, you're limited with the amount of volume in that space. So in this example, we have one VRV system serving 12 spaces. Bedrooms 1 to 6 are micro hotel rooms, so 80 square feet. And bedrooms 7 through 11 are average North American sized hotel rooms, so around 200 square feet. And then the meeting room has a 750 square foot floor plan. VRV system is an 8-ton containing 50 pounds of R32. Again, R410A would be a higher charge. 12-port multi-port box with medium static ducted fan coils, 7,000, 9,000, and 24,000 BTUs. Again, we've lost the animation on the next slide. But without safety mitigation, the hallway is the only space that's under the refrigerant concentration limit. If we're able to bring on the fan with a refrigerant leak, the meeting room and the hallway are both compliant. If we're able to apply those safety shutoff valves at the branch selector box or the branch controller box, all of a sudden all of the rooms are compliant with the refrigerant concentration limit because the releasable charge in those spaces is below that level. Arguably, with the shutoff valves at the branch selector or branch controller box, really the total system charge is not applicable because we're only looking at the refrigerant charge downstream. So this example was an 8-ton, but it could have easily been a 20-ton or a 30-ton system and still be compliant. I do get a lot of questions around existing R410A systems. So what about the systems that were installed last year or systems that are due to be installed next year? The good news for us is that the California Regulatory Board has gone ahead and given us some parameters on replacement of that equipment. So although we're moving to no or low GWP refrigerants in new systems as of 2026 in the US and potentially 2027 in Canada, The existing systems that are out there will be able to be serviced and repaired for the foreseeable future. So what that looks like from Daikin's perspective is that we will continue to manufacture R410A products for replacement market. The condition is that those products, when they come into Canada, will have a specific label that says that they're for replacement market only, so they cannot be used in new installations. CARB has said that you can replace up to 75% of indoor units and all of your outdoor unit components within a 3-year time frame and still not be considered a new system. If you exceed that limit, then you're getting into lower GWP refrigerants, so now you're going to have to switch over to either the R32 or an R454B product. When we're talking about VRV and VRF systems in general, roughly 2/3 of the cost of those systems goes towards the piping and the infrastructure in order to support it, and 1/3 is the equipment cost. And the good news with the R32 products is that we're using the same refrigerant oil, so it's a PVE oil, and for the most part it looks like the piping diameters would be very similar. So it brings into the feasibility of reusing most of the infrastructure in place, even if we go to replacing the entire system with a low GWP alternative. So just in closing, R32 is the most balanced, globally proven refrigerant choice that's designed for total cost of ownership. It takes into account not only the GWP of the refrigerant itself, but the charge size, energy efficiency, serviceability, application flexibility, and it's not proprietary. And that's everything I have for you. So is there any questions? No questions? Yes?
How significant is recycling? What kind of leakage? Thanks. What kind of leakage do you see in recycling of the refrigerants?
The recycling of R410A is not, like, there's not a big industry for that right now, and that's partially because of the cost of it hasn't really seen a huge increase. But what will happen as the phase down continues and becomes less and less new refrigerant into the market, recycling is going to become a key component in maintaining the availability of R410A in the product in the market. R32 is much easier to recycle because it is that single component, so it's not, you don't have to worry about splitting out the blend and then remixing it. It's just a single component, so it can be reclaimed easily, cleaned, and sent back out to the market. Okay, well, thank you very much.